So vector operations is what we're going to talk about. Now, in particular, I'm going to start with addition. And if you think about it, for some of our parameterizations that we talked about, we took advantage of what we know about vector addition. So for example, I'm just going to review briefly, we had that thing called the cycloid, right? We had that wheel rolling around, right? And what did we do? We were interested in a point that was somewhere on the circumference of that circle. Actually, that one wouldn't be there. That would be over here, right? Well, actually, it probably would. It would roll up from around there, okay? And if you think about it, there were three vectors that we added together in order to build that parameterization. Select. So the first of those vectors went from here to here, okay? So we'll call this O, right? And that kind of thing. And then while we're at it, we might as well state the vector we're interested in. We're interested in that vector, okay? And that vector I'm going to call OP. Right? Then there was actually two more that we were interested in as well. Correct. So we were interested in this vector, the vector that would take you from the x-axis to the center of the circle. So maybe I'll call that point C, and then we'll call this, I don't know, I don't want to call it x, I'll call it t maybe. And then lastly, the third vector, which took you from P to C. And what we said is that the vector OP, the one we're interested in, was equal to the vector OT plus the vector CT plus the vector CP. Okay? And we took advantage of that, and if you look in the, look back in your notes about the cycloid and how we got its equation, we used this idea. This idea of adding vectors, we sort of call this tail to head, right? What you do is if you want to add two vectors, if I have a vector A over here somewhere, and then some other vector B over here, and I want to add them, then the process is you pick up vector B, and you take its tail, and you put it here on the head of A. So there's vector B, okay? And what we know is, if we arrange that, then the vector that starts at the tail of A and points to the head of B represents the sum of those two vectors. Okay. Now, in your textbook, just so you know, and you should know this because you notice sometimes I write vectors, I put like these little arrows above them. Some textbooks will put little things like this above them to indicate that they're vectors. Your textbook doesn't do that. Your textbook just bolds them. It makes like a bold letter, bold font, and that means a vector. You'll know by the nature of the problem that the thing you have has components, and then you're adding them. Okay. So you can kind of see, especially in the case of this parameterization up here, that the tail to head method for visually representing the sum of vectors is very nice. And it helps you out in a lot of situations. Okay, there's another method you may have learned about in your physics class, right? Making a parallelogram? Right? Maybe. I don't know. So for example, if you're going to add vector A, and then you're going to add vector B over here. Okay, what did you do? In essence, it is just like tail to head. You pick up vector A and you sort of complete the vector B, that is, and vector A right over here. You make copies of them, and you complete the parallelogram spanned by those vectors. Okay, and then you're interested in the diagonal. Okay. So people might say, this is really not that big of a difference. This kind of diagram that you're looking at now has like one maybe nice application. You can kind of think of it the following way. Imagine there's an object here that's very heavy, right? And we want to move it. So maybe someone comes along and tries to pull this object. And let's pretend they're pulling in the direction of vector B with the magnitude of B. So this vector B might represent a force with a direction. And then also, the person maybe not be able to move it by themselves, or some other person comes along and says, I'll help you out. And they kind of help you in an awkward way because they're not as strong as you, because their magnitude, the magnitude of vector A is not as big as the magnitude of vector B. And they don't quite pull in the same direction as you either. They pull a little bit. Off on another angle, so to speak. And what happens is that the path you end up traveling along, this object gets dragged along, is represented by this blue vector, which is a plus b. Okay? So that's sort of like a nice time to think about parallelograms. Okay. Now, I want to look at this picture again and just make another comment about this. Let's just redraw it. I'm going to leave out the sum. And here we go. So we'll copy this vector up top. Picture is going to look very similar. Here's vector B. Here's vector A. And my question to you is, if you look carefully in this picture, you can actually see the vector A minus B. So the question is, where is it, right? And where does it point? So let's be specific about that. Think about that for a minute. So the vector A minus B is the other diagonal. And the only thing you got to just be careful of, right, is which direction it's pointing, right? Now, it's pointing at A. This is the vector A minus B. Looks like I'm just drawing arrows. I'm so happy to draw them. There it is. A good question for you to think about is, why does it have to point that way? And how come it doesn't point from the from the tip of A, or the head of A, to the head of B? How come it doesn't point the other direction? To do this, let's just take this picture. I'm going to just move it a little bit over here so I have some room. Here's the vector B. Here's the vector A. And we're trying to sort of justify why this vector should point like that. This is the vector A minus B. Okay. And with that, here's a way to think of it, is to start to think about what this must look like. Suppose I asked you about the vector negative B. What do you think that looks like? Yeah. And the vector negative B is just like the vector B, except it points in the opposite direction. So I'm gonna situate it right here. Now, let me just talk about just one thing to be clear. I have sort of a freedom. When I say, hey, what's vector negative B look like? I drew it in green right here. Vector negative B does not have to have its tail touching the tail of vector B. Okay? I can make many copies of vector negative B and sort of just drop them all over this page. Okay? So these are all the vector negative B. A vector does not have to be in a particular location on the plane. All right, so now, the reason I asked you to consider that is because when we're trying to find this vector, A minus B, you can consider instead the vector A plus the negative of B, right? Or consider that, just computing that, and you'll get the same result. Well, if we do it that way, then here we go, right? Here is vector A. Here's vector negative B. Let's use our parallelogram method if we want to do that. Or we can use our tail to head method. So we could take vector negative B, for example, and copy it up top. And if we do that, here's what it would look like. Here's negative B. And then clearly, the sum of A plus the negative B looks like that. Okay. Well, there you go. Now you can see that this new vector I just drew, an A plus the negative B, is really the same vector as A minus B. So that sort of confirms why this thing points the way it does. Okay? Is there another way to sort of think about why vector A minus B has to point the way it does, has to point from the head of B to the head of A? To justify that this vector points from the head of B to the head of A, the vector A minus B, this vector here, you can think of that in the following way. I mean, we write A minus B, but I guess what are we trying to find? We're trying to find a vector where this equals a vector, or equals the vector we can add to B to get A, right? If you think of it from that like conceptual point of view, right? I'm saying the vector A minus B is the vector that we can add to B to get to A, then you know it would have to point from the head of from the head of B to the head of A. So that's like an intuitive way to reason why this vector has to point the way it points. So like I said, what I want to do next is try and make a transition from this geometric way, this pictorial way of adding vectors, to something algebraic, some algebraic equivalent. So what I'm going to do is I'm going to take, I'm going to do a couple things here. I'm going to draw this vector here. Now I'm putting this on a grid to be specific about things. I'm going to call this vector A. And up here somewhere I'm going to put vector B. Okay? Now, if I intend to add those, which is my goal, if I want to add these things, then one option I have is to pick up vector B and put its tail at the head of vector A, right? Or vice versa. Sort of fun to think about. Or I could use the parallelogram method, so to speak. I'm going to do that. All right, so vector A, I'm going to make a copy of it over here. Here's vector A. How do I know that's a copy of it? Because this vector was over 3 up 1. And that's what I just drew here. Okay, so here's vector A. I'm going to take vector B, and that's over 1 up 2. So I'm going to do the same thing here, over 1 up 2. Put it like that. Here's the vector B. So let's just highlight these things. So I went over 3 up 1, over 1 up 2. Okay? And parallelograms have the property that opposite sides are parallel. They have the same slope. So we know when we complete our parallelogram, for example, this vector B, which is over 1 up 2, would have to be over here, over 1 up 2. So it would point to that point. There it is. And then vector A is going to be over 3 up 1, so it would go like this. There's vector A. And we're interested in the diagonal of that parallelogram. Well, if you look at it carefully, what you can see is you can see that to go from the tail of A to the head of A, we had to go over this 3 plus that 1, right? And then we had to go up this 1 plus this 2. So in other words, here we're ready to make the transition to something algebraic. The vector A can be expressed this way. It's the vector 3, 1. And the vector B can be expressed this way. It's the vector 1, 2. And what we've just shown is, that the vector A plus B, you can arrive at that just by adding the changes in the horizontal direction, so this change of 3 and this change of 1. So that's going to be 3 plus 1. And then we could add our changes in the vertical direction, so 1 plus 2. So we get the vector 4, 3. Okay. Not so bad, right? Okay. Sort of a fun thing to think about now is, right, we've got this new idea of vector addition. Could we add in either direction? And we know addition of real numbers is commutative. You would think this is commutative. This picture sort of tells you the story, doesn't it? Right? I can go over 3 up 1 and then up 1 over 2. Or I can go up 2 over 1 and then up 1 over 3. And if I do that in either order, I will end up landing in the same spot. So that means that vector addition is commutative. Now, vector subtraction isn't commutative. And we know why, right? If we think about our picture from before, there's a couple of ways to think about it. But if we think about our picture from before, here we are. We spent a lot of time talking about why A minus B would have to point from the head of B to the head of A. Turn it around. What if I asked about B minus A? Well, that would be the vector that we can add to A to get to B. Oh, it's the vector we add to A to get to B. That means we have to start at the head of A and point at the head of B, which is exactly the negative of the vector A minus B, right? Now that's sort of interesting that it's consistent with what we expect in the real numbers. I mean, back in the real numbers, if we start taking things that, like for example, 5 minus 3, we get 2, and 3 minus 5, we get negative 2. And now it just sort of reasoned out is that the subtraction of vectors works the same way. Okay? Let's just formalize things a little bit, right? So if you have a vector, we'll call it v1, whose components are a1, b1, and you have another vector v2, whose components are a2, b2, then the sum v1 plus v2 is just a1 plus a2, comma, b1 plus b2. Okay? Just as a comment, sometimes in other textbooks, instead of seeing a plus here, you'll see like a plus maybe circled, or a plus that's like bolded somehow. And they're just trying to remind you that you're adding vectors, you're not adding numbers. It's a different kind of addition. Okay. One more quick thing. Suppose I take one of these vectors. I'll say this. I'll say let C be a constant or be a real number. And I ask you, hey, what about this vector? C times the vector v1. All that means is you multiply the components of that vector by your constant, whatever it is. That's all it means. And in effect, all that does to your vector is it like strings or stretches it, or could even change the direction of it. So for example, here's your vector v1, right? And it has components, a component this direction, a1, and a component this direction, b1. If I multiply by c equals 1, I get back the same vector. If I multiply by c equals a half, then I would get this vector. So that vector right there, the blue one, is a half of v1. If I multiply by negative 3, or let's just do negative 2, because I don't think negative 3 up on the page, I've got this distance here. It would probably be something like that. That should be twice as long, but in the opposite direction. There's negative 2v1. There's that vector. So that's the effect of multiplying by a constant. Okay? So let me just give you a property of vectors and show you how to prove that. And you'll see how to do these proofs when you have component-wise addition and things like that. All right? So here's a property that's supposedly true. It says that if you have a constant c, all right, so let's make clear that this is a constant. It's not a vector quantity, okay? And we're going to multiply it by a plus b, where a and b are vectors, okay? Then you get c times a plus c times b. All right? Now, your textbook does a better job than I do drawing this for you, right? My C's and my A's and B's all look like the same font, but in your textbook, I promise you the A's and the B's will be bolded, and bolding means they're vectors, right? And just the regular font letter is going to be a constant, or just a number. Okay. So how would you show this? All right, so here's how you could do it. Let's we'll say this. We'll say let vector A equal the vector A1. Yeah, you could do anything you want. I'm going to do A1, A2, A3. We'll prove this for 3D vectors, and then you'll be able to convince yourself pretty quickly it would work for any dimensional vector. Okay? And then we're going to say B is this vector, B1, B2, B3. Okay? And I guess what we're going to do is we'll start with one side of this expression. We'll start with this side, and we'll keep working with it until it looks like the other side. And then we can say, oh yeah, look, everything's fine. Okay. So what does it mean to multiply by a constant? We just discussed that. We multiply all these components by that constant. Okay? But that's not really what we're asked to do first. Here we're being asked to add first, so we have to do that. So we're going to have C times the sum of the vectors. So the sum of the vectors would be that you add them component-wise. So the first component is going to be A1 plus B1, comma. The second component, those were those two right there. Now we're going to add these two. So we get B1 plus B2, comma. That's my mistake there. Hold on a second. This should be A2 plus B2, Okay? And then this should be A3 plus B3. Okay, good. Yeah. So, all right, fair enough. What does it mean to multiply by a constant? It means we multiply every component by that constant. So if we do that, we get the following. We get C times this component, comma, C times that component, and C times that component. Okay. Now, I'm actually very happy right now because when I look at this, what I notice is inside of each component is just something I know how to handle, right? This is the distributive property because A1 is not a vector anymore. A1 is a number, and B1 is a number. And I know the distributive property holds for multiplication over addition. So I have the ability to do this. I can say that this is really CA1 plus CB1. And I'm allowed to do that now because A1 and B1, these guys right here, are numbers. So it's one of those things, it's very important when you look at these things. Pay attention to what you're writing on the page and ask yourself when you write every variable down, is that a vector or did I just write a number or a constant or something like that? Okay, and then watch this. Then you get CA2 plus CB2. And then this is CA3 plus CB3. So I got to use the distributive property. So the distributive property of real numbers. And actually, that turns out that saved me. Because now, this I can really think of as the sum of two vectors. This is the sum of the vectors CA1, comma, CA2, comma, CA3, plus another vector, CB1, comma, CB2, comma, CB3. And once you agree that these two expressions are the same, then you're kind of home free now. Because this, the more compact way to write this is just write CA, where A is a vector, plus this is really CB, where B is a vector. That's exactly what we wanted to prove. So that's how these proofs work. You usually start out by writing out the components, deciding what you want to call the components, pick any notation you want, and then work with one side, proceed through, and just carefully split things apart when you want so that you end up looking at an expression which is what looks like the right side of your equality.